Okay, we're ready to go. The H-man cometh. Today we're talking about factoring. Factoring in a few different special cases. The difference of squares factoring and the sum and difference of cubes factoring. So first, when you're factoring polynomials, when you're factoring anything, don't forget to look for a greatest common factor. That is going to make your life easier. It's going to make the numbers that you deal with a little bit smaller. Okay, so always look for a greatest common factor whenever possible. So you should already be familiar with these formulas. I'll show them here on the board. We have the difference of squares, the sum of cubes, the difference of cubes. Make sure that you know these formulas before watching this video. Now, you don't have to be an expert at them, but make sure you've seen them in some capacity. You've written them down somewhere you can practice them constantly. Okay, but hopefully after this video, you're going to be able to remember how to find the factors in a situation with difference of squares or sum of cubes or difference of cubes. Now, the way that I introduce this formula to you, I don't really show you the straight up formula. I'm showing you where it comes from. And when we multiply binomial with another binomial, and the difference in these two binomials is only the minus sign in the middle and the plus sign in the middle on this factor. So if you FOIL all of that work out, rest assured that these two middle terms are going to cancel. And so we'll be left with a squared minus b squared. That means if we're trying to factor, which takes us backwards in the reverse order, we need to be able to identify, see how I've underlined this in red, what is our a and what is our b. As long as we can find what our a is and what our b is, we can simply replace those into this factorization, a plus b times a minus b. Okay, so we'll get some practice with doing that in a moment. Similarly, sum of cubes, first I take us through multiplying this. So you should work this out. You should multiply this out for yourself. And that will reinforce this formula. Multiply this out for yourself, which I've done here, and you'll see that these middle terms cancel again. And the result is a cubed plus b cubed, which is why we're referring to this as a sum of cubes. See that the middle terms cancel. And notice the format. We have a plus b and then we have a squared minus ab plus b squared. So again, as long as you know your a and your b, if you can identify your a and your b, when they give you an expression like this, you need to be able to identify two things. You need to be able to identify the perfect cube, and then you need to identify what it is that's being cubed. What's your a and what's your b? And once you do that, you can just put it into this form, which requires you to memorize the form. And there's some tricks for that. We'll get some problem with a sum of cubes. Now, similarly, we have a difference of cubes. There's really not that much that's different in this than the formula for the sum of cubes. The big difference, the sign here is a minus, and the sign here is a plus. Notice that this one is always a plus. So I'll go back to the sum of cubes to show you that. In fact, I can kind of zoom out, and you'll see the similarities. We have a plus b in the sum of cubes. We have a minus b in the difference of cubes. Kind of makes sense, sum and difference. Now we have the opposite symbol here. The minus is opposite of the plus. And the plus here is opposite of the minus. So those are the differences, and the outcome is also different. So in the sum of cubes, we end up with a sum of cubes. Of course, a cubed plus b cubed. Whereas in this difference of cubes, we end up with a cubed minus b cubed. Okay, so we're going to do some examples which allow us to practice these skills. For example 1, we're going to keep it simple. We're going to work on a difference of squares problem. And I'm not really spoiling too much by saying it out loud that it's a difference of squares. You can tell in this case because this is a perfect square. And we have subtraction. So, wow, that was a really bad arrow. So we can call this a difference of squares. And that means that we have to identify this as our a squared. And this is our b squared. So you have to ask yourself, what thing multiplies to itself in order to give us what's up here? What thing multiplies by itself to give us 4? That would be 2. Okay, but we're not done because it's not just 4, it's 4x squared. What multiplies itself to give you x squared? Well, that's just x, of course. So our a value is 2x, and our b value, what multiplies to itself to give 25? That would be 5. So we found our a minus b, we found our a and b. We're going to plug that into the format a minus b times a plus b. For those of you who are curious, is this the exact same thing as a plus b times a minus b? Yes, it is. Very important note here that the order of multiplication does not affect the result. Okay? So this would be the same thing as if we were to call it a plus b, a minus b. Okay, so let's just plug in our a and b. Enough dilly-dallying. This is 2x minus 5 and 2x plus 5. And that is the factorization. Okay, pretty solid. There was no GCF here, no greatest common factor, because 4 doesn't have anything else but 2's in it, and 25 is not made up of anything else but 5's. It's just 5 times 5. So there's no common factors to remove beforehand. All right, let's take a look at the next example. It's going to give you the opportunity to practice the sum of cubes. Oops, did I give it away? Yes, I did give it away. That's okay. The reason why is because I'm not trying to trick you here. I'm just showing you how these are used very simply. I'm showing you the simplest way to do these. That is the goal in these problems. So we see that this is a cubed. So it's a very good idea to think that it's going to be some kind of cubes factoring. We see that there's a positive, so that would be a sum of cubes. Then we just have to make sure that this works as a cube. Is this a perfect cube? Could this possibly be my a cubed? And could this be my b cubed? Well, yeah, it could, because something times itself to give us 27. You guys should know some of your very low number basic perfect cubes. So basically from like 1 to 8, I think you should probably know. 1 to 6 at least. I mean, that's not too much to ask, honestly, guys. You won't often get anything higher than that, but just to be prepared, it's not that much. And if you see that it ends with a certain number, like an odd number, you can only try odd numbers. If you see it ends with an even number, you can only try even numbers, so that even limits the amount of guesses that you have to make. Okay, so 3 times 3 times 3 gives us 27. And what about x cubed? We have to keep that in mind as well. So this would be x, because x times x times x gives us x cubed. Now for the b value. And this is not even the difficult part, I would say, of the sum of cubes. Really, it's memorizing that formula. But you need your a and b to know that formula, to be able to use the formula. So for the sum of cubes, we have to remember that it's going to follow the same sign in here. And it's going to be opposite, always positive. In fact, there's an acronym for this. They call it SOAP. And it stands for same, opposite, always positive. And that's a way to help you remember what signs are going to go inside of here. So we have the same sign, it's a sum of cubes. So sum is plus, opposite, negative, always positive at the end. Now what goes in here, this could be kind of tough, but just start with the power of 2. Imagine you have 2 choices. You have 2 choices, okay? Now for the first option, you're going to make both choices be a. So you're going to choose a, that's a squared. Then for the next one, you're going to be fair, and you're going to go a and b. So a times b. And then for the next one, you're going to be picking the b twice, b squared. That's not so hard to remember, right? So first time, both picks go to a. Then you're trading one of the picks for b, and then you're trading the other a pick for b as well. So this is the factorization. Let's plug in the values. We have 3x plus 2 times, we have to do a little bit of work here. A squared means 3x times 3x. Do not put 9x, it is 9x squared. Minus ab, which is a times b, that's just 3x times 2. 6x plus the b squared, which is 2 squared, that's 4. And this is your complete factorization. Okay, so using this acronym SOAP kind of helps us out a little bit. You don't have to remember the acronym, you can just remember the formula, but this is a way to help you remember what positives and negative signs go. Okay, moving forward to example 3. Example 3, let's take a look at what we have here. 5x cubed minus 20x. I want you to factor this completely. Okay, so you might say, oh, we have an x cubed, so that's probably a good idea. That's going to be a perfect cube. But then I take a look at 5, and I say, hey, wait a minute. 5 is not a perfect cube. I know that for sure is not a perfect cube. And also, this would not be a perfect cube, because this is an exponent of a 1. So this would not even be a perfect cube. And 20 is not even a perfect cube. So let's think back to the basics. I mean, do I have to say it? You can read it, right? Yep, that's right. We got to look for a GCF. So let's look for a greatest common factor. And there is clearly common factors here. They both have x involved. So that's a common factor. Let's remove the x. But also I can divide something else. I can divide 5. And if I do that, I'll be left with x squared here because I took the 5 and I took one of the x's. There are 3, took 1. And here I took out the x and I divided out the 5, so this is left with a 4. Ah, okay, we see where this is going now. This is looking more like a difference of squares because that's an even number, which is a squared. This is a perfect square. 4 is a perfect square. So I'm thinking we're going to have to do some difference of squares business here. We're going to have a equals x. Also, there's a minus sign here, so that's a difference. B equals 2. And so we can just use that nice formula. A minus b, x minus 2, a plus b, x plus 2. And this is factored. Now, in all of these cases, I'm just having us factor it. I'm not having us solve. If these said equal to 0, right, like if this said to solve it and said equal to 0, you would just take this, set it equal to 0, and then you would have to solve each of these equal to 0. Like you would put 2x minus 5 equals to 0, 2x plus 5 equals to 0. And you would get some solutions here. You'd have x equals 5 halves, and you'd have x equals negative 5 halves. Those would be your two solutions to this original equation. Meaning if you plug those x values, not at the same time, of course, if you plug either one of those x values in, those are some ugly looking 5s. If you plug either one of those in, 5 halves or negative 5 halves to this equation here, then you're going to get 0. Now, why do I bring that up now? Because when you do a sum of cubes or difference of cubes, I forgot to mention this. This will not have any real solutions. No real solutions. So if you're trying to solve that, just in this part, if you're trying to solve that, in this part here, you will not have real number solutions. You will have to use the quadratic formula. Do not try to factor that anymore. Do not try to factor that anymore. Okay? So there will be no real solutions there. In fact, I should probably make a note of that here, but it's not really too important because these are not solving equations. But I did want to mention that if you're solving equations, do not try to factor this down more. It's called an irreducible quadratic. You cannot factor it down anymore, even if it looks factorable. Okay? And I also bring that up because if this were equal to 0, and we were solving, then you would set each of these three factors equal to 0. Okay? Let's move on to one that is a little more interesting here. Is that the one? Yeah, that's the one. Example 4, I guess we can call this. Yeah, we're moving along. We're going to say, maybe I should move it up here. 64 x to the 7th minus, oopsie, 125 x to the 4th. So what's the dealio here? What's going on here? It's not really a difference of squares, we can tell, right? It is subtraction. It might be a difference of something. But we don't see squares because even though this is a perfect square, this is not a perfect square. 7 is not an even power, so it can't be a perfect square. So what do we do? GCF. We have to take something in common. These have x's in common. How many? They have 4. And that will leave us with 64x cubed minus 125. And now this is finally starting to look like a difference of cubes situation. So we just have to double check and make sure. Is 64 a perfect cube? And this is why I want you guys to know. I want you guys to know your perfect cubes up to at least 6. Like, come on, that's not asking too much. 1, 2, 3, 4. I mean, 1 is for free. 1 cubed is 1. They're pretty simple, right? And you can multiply them out if you need to. Get good with them for a while. You don't have to keep them in your memory for like your entire life. You don't have to name your kids after like 5 cubed. But just know it well enough for this exam, right? It's part of the challenge of this exam. Okay, so if that is my a cubed, then hopefully by now you've worked out that a equals to 4. And again, like I said, if it ends with an even number, just try only even numbers. So just try 2 and then 4, and then you already get it. This one ends in an odd number. It ends in a 5, which means it has to be a power of 5. Now, I don't expect you to know that. You don't have to know that. But if you were to try 1, obviously 1 cubed is 1. 3 cubed is 3 times 3 times 3, 27. And then the next one that you try is 5. Something else about this a value. It's also x times x times x makes x cubed. So there is our a and b. Okay. You might be wondering what's going to happen with this guy. This dude is just going to chill and wait for this whole difference of cubes factoring. Just going to sit out front. Just hanging out. Okay, let's do a minus b because it's a difference of cubes. So 4x minus 5 times a squared, which is going to be 16. That's 4 times 4. X squared, that's x times x. Plus a times b. So plus a times b. Remember, SOAP. Same sign, opposite sign. This is going to be 20x. That's 4x times 5. And then always positive, b squared. 5 times 5. 25. Okay, so this is the full factorization. Not too bad. We're really just using formulas here. So like I said, I want you to have looked at the formulas ahead of time and then get very comfortable with finding a GCF. Look for a greatest common factor. Right. Now let's do a repeated factoring problem. Yeah, okay. Example 5. I want you to factor x to the 12th minus x to the 6th. Now, what are you going to call that? This one is quite interesting because there is more than one way that you can look at this. Some of you might immediately say it's a difference of squares. That's pretty good thinking right off the bat. And I think it's pretty natural to think that as well, because we have these even powers. Even powers means we have squares, basically. Something that's to a power 2 raised to a power 2, it's going to have an even power. So difference of squares is a great way to approach this. You could also see this as a difference of cubes, which is not obvious, but let's just go with the difference of squares route for now. So if this is a difference of squares, that means this is my a squared, and this is my b squared. Therefore, my a is what? Try and think about, what is my a? If x to the 12 is a squared, what is my a? Then my a has to be half of that power, x to the 6th. And if you don't believe me, I'll just kind of show you right here. A squared would be x to the 6th squared, and the rules of exponents say that I would multiply these exponents. So this is x to the 12. So that just shows that if you cut the power in half, you're looking at the square root, basically. So similarly, for the b value, we're going to have that this is x cubed. Okay, so how does this factor exactly? It factors to a minus b times a plus b. So let's do that. X squared minus x cubed times x, sorry, did I say x squared? X to the 6th minus x cubed. I was thinking a squared, which it's not even a squared, it's just a minus b, a plus b, and x to the 6th plus x cubed. Now, do these strike you at all as interesting? Well, it looks like it might be another difference of squares because this is an even one, but this is not an even one. That's a 3. So it's not a difference of squares, but it is a difference of cubes. This one is a perfect cube, and this one is also a perfect cube, which means that this is a perfect cube and this is a perfect cube. So we have ourselves a difference of cubes on the left and a sum of cubes on the right. If you still can't see it, let me take a second to break this down. If this is my a cubed, just like we thought about earlier, how would I find a? Instead of dividing the power by 2 like I did for the squared, I would divide the power by 3. So that's going to give me an a value of x squared. And again, I'll just show you really quickly that if you have a cubed, that would be x squared cubed, or to the 3rd power. And again, the rules of exponents says to multiply these. So there you have it. That's x to the 6th. Well, if this is my b cubed, then of course b is just x. But that means that I have a cubed minus b cubed, and then I have a cubed plus b cubed with the same a and b. So fortunately, I don't have to find the a and b for this one and then find a different a and b for this one. Fortunately, I do not have to do that. But I still have to open up these factoring formulas, kind of. I have to expand these difference of cubes and sum of cubes, and so that's going to get a bit large. Okay, so let's go ahead and do that. Let's move this thing here. What is that going to look like? I want you to recall. Go into your memory right now. Like, think. If you have to close your eyes to focus or whatever, I don't care. That's fine. A cubed minus b cubed. How do I factor that? A cubed minus b cubed. It's a difference, so there's going to be a minus b times a squared plus ab plus, always positive at the end, b squared. Okay, so hopefully you created a little mental map. You're taking your mind to that place where the formula exists when you need to use it. Okay, that's what learning, that's a part of learning anyways. That's not all there is to learning, but that's one component of learning, is going somewhere in your mind with the information, storing it there, putting it somewhere safe, like a dog does with the bone, but except you got to remember that the bone is there. Sometimes the dog doesn't remember that the bone is there. Okay, so let's do that with plugging in x squared. X squared minus x x squared squared. That's my a squared, okay? So think about this carefully. A is x squared. Right up here. Don't get lost. A is x squared. A squared is x squared squared, or in other words, x to the fourth, plus we have x times x squared, that's x cubed. And then we have x, which is from b squared, that's just going to be x squared. Interesting. And there's a reason why this comes out to have so many common factors. I'll explain that in a moment. So there we have it so far. Now let's do the same thing for this sum of cubes. I'm going to skip down to the bottom right away. A sum of cubes is going to be a, which is x squared, plus b, which is x, times a squared, so x4, minus ab, so x squared times x, that gives me x cubed, and then plus b squared, which is x squared. This is the factorization, and if you notice, they all have GCFs in them. Why is that? This one has a GCF of x. This one has a GCF of x squared. This one has a GCF of x. This one has a GCF of x squared. If I take all of those out together, x and x squared, that's 3 so far, another x squared, that's 3 more so far, I take out x to the 6th, and I'm just left with this. X minus 1, x squared plus x plus 1, x plus 1, x squared minus x plus 1. Oh my goodness. Isn't that something? The reason why we had these common factors at the very end was because in the beginning, if we would have looked at this using our rule, don't forget to always look for a GCF. My whole point is that when you look for a GCF, it makes things easier and it saves you time. So let's look at how quickly we could have solved this. If we take out x to the 6th right from the get-go, we are left with x to the 6th minus 1, which may not look like a sum of cubes necessarily right off the bat, or a difference of cubes right off the bat, but it is a difference of squares and it is a difference of cubes. If you would like to look this as an even power, because it is, and it's a difference of squares, or if you like to look at this as a multiple of 3, because it is a multiple of 3 power, and this is now a difference of cubes. So let's break this up using the difference of squares first. This would be easiest. That's x cubed minus 1, x cubed plus 1, and then hey, look at that. There are our formulas. So we go straight to the difference of cubes formula. X minus 1, x squared plus x plus 1, and then for the sum of cubes formula, x plus 1, x squared minus x plus 1. So hopefully that shows you how useful finding a greatest common factor and taking that out first is, because then it saves this sort of more tedious headache that we had to go through here, and then we had to factor out all of those common factors and not screw anything up along the way. You can see the difference. Much better to just take the greatest common factor out from the get-go. Okay, so hopefully this was helpful. This is just a brief summary of some factoring techniques, these two particular ones. You should practice them. There are plenty of practice exercises online. If you look up difference of squares practice, sum of cubes practice, difference of cubes practice, and they can get progressively harder than this. There wasn't too much tricky substitution that we had to do anywhere. It was very straightforward. So these are just the basics. This is considered like a level 1 or level 2 out of 5. So if you want some much more difficult examples, you'll have to scrounge the internet a little bit harder for something like that. Or perhaps in the future I'll make a video for that. Maybe something that reflects like an honors level testing of this topic. But there will be a follow-up video to this, which covers more work with polynomials, including polynomials sort of this type, which I mentioned are irreducible. We will look at the process for finding non-real solutions of quadratics, but that is for another time. For now, we're signing off. Hope you learned something. See you next time.